What really happens when continents collide? How do forces deep within the Earth bend solid rock, crush ancient oceans, and create majestic mountain ranges? And how has this process of continental to continental convergence reshaped our planet's surface through time? Stay tuned, because today we're time-traveling across four incredible continental collisions, resulting in the formation of the Himalayas, the Alps, the Appalachians, and the Urals. Welcome to Earth Diary. If you enjoy learning about geology and Earth's hidden history, make sure to like, subscribe, and stay till the end. Continental to continental convergence is one of the most powerful geological processes on Earth. Here, two continental plates collide after consuming the ocean that once separated them. But neither one sink into the mantle, as both are too buoyant to subduct. The result isn't volcanism, but compression, folding, faulting, and uplift of the continental crust. Here, rocks are metamorphosed under intense pressure, and they fold, thrust, and push slices of crust miles from their original positions. This leads to thickening of continental crust, sometimes exceeding 70 kilometers, forming majestic mountain ranges above the surface and deep roots. The scar, where the continents finally weld together, is called a suture zone. These zones often preserve fragments of the vanished ancient oceans known as ophiolites. Collision zones are also hotspots of powerful earthquakes generated by the stress and deformation of the thickened crust. Yet despite all that energy, volcanism is rare or absent, because the thick continental crust resists subduction, leaving little molten magma to fuel volcanoes. As time passes, erosion and uplift work together and expose once deep metamorphic rocks. This is the fundamental framework on which continental convergence operates. Yet, every collision tells its own story, shaped by the rate of convergence, the degree of crustal thickening, and the way each origin evolves through time. Let's start our journey with the most dramatic collision on Earth today, the Himalayas. Around 50 million years ago, two massive continental plates, the Indian and the Eurasian plate, collided in one of the most dramatic tectonic events in Earth's history. Between them once lay the Tethys Sea, whose ancient sediments, layers of sand, mud, and limestone, were squeezed and folded into a thick wedge as the plates converged. When the two continental plates finally met, subduction came to a halt. Instead of one plate sinking beneath the other, the crust crumpled and welded together along the Indus-tsangpo suture zone, marking the final disappearance of the Tethys Ocean. This high-speed, head-on continental collision, that is also the fastest convergence on Earth, thickened the crust by nearly 500 kilometers. It forged a deep crustal route beneath the region and lifted the tallest mountain range in the world, the Himalayas, with peaks soaring over 8,000 meters. As immense pressure built, massive thrust belts formed. The main central thrust, MCT, the main boundary thrust, MBT, and other major faults stacked crustal rocks atop one another, giving rise to the Greater, Lesser, and Siwalik Himalayas, a spectacular system of fold mountains. Limestone once deposited on the Tethys ocean floor was pushed skyward, now crowning Mount Everest itself, a stark reminder that these towering summits were once beneath the sea. But the story doesn't end there. The collision caused extraordinary crustal thickening over a vast area, both vertically and horizontally, uplifting the highest and largest plateau on Earth, the Tibetan Plateau, averaging 4,500 meters above sea level. Because of their young geological age and rapid uplift, the Himalayas remain geologically active, producing frequent earthquakes, some exceeding magnitude 8. Yet, unlike oceanic collisions, there are no volcanoes, only a still active continental collision that continues to push the mountains higher at roughly 5 centimeters per year. Meanwhile, mighty rivers carve through the rising terrain, cutting deep valleys and balancing uplift with erosion, continuously reshaping this young mountain system. The Himalayas, in every sense, are a landscape still under construction, young, restless, and growing. Now let's travel west to Europe, where the process of continental convergence has also shaped the land, slowly, through a more complex and layered history. Around 65 million years ago, during the Cenozoic era, the African plate began its slow march northward. The resulting collision compressed the crust with immense force, uplifting it to form the majestic Alps. Both the Alps and the Himalayas formed from the closure of branches of the ancient Tethys Ocean, but the Himalayas soar higher, driven by a faster convergence rate. While both ranges began forming around the same era, their main uplift phases differed. The Alps rose between 55 and 35 million years ago, whereas the Himalayas began about 50 million years ago and continue to grow today. The Alps grew in multiple stages. Over millions of years, small continental fragments and remnants of ancient ocean basins known as microplates were gradually squeezed and welded together between Africa and Eurasia. The strong compressional forces created naps, huge sheets of rock, where layers of crust were pushed over each other for hundreds of kilometers. These folded structures shape the Alps and can be seen in famous peaks like the Matterhorn. Today, the Alps are moderately high, with peaks like Mont Blanc reaching about 4,800 meters. Beneath their surface lies a complex internal structure. The range is now tectonically mature, rising slowly, about 1 millimeter per year, and experiencing only moderate earthquakes. If the Himalayas represent raw, unstoppable power, the Alps symbolize tectonic intricacy, a mountain range shaped by repeated collisions and the slow, careful reworking of the Earth's crust over millions of years. Next, let's travel even further back to the Paleozoic era and witness an ancient collision that once built another mountain range as tall as the Himalayas, the Appalachians. Over 300 million years ago, during the assembly of the supercontinent Pangaea, an ancient ocean known as the Iapetus Ocean began to close. The Laurentian Plate, what is now North America, drifted toward Gondwana, the landmass that included present-day Africa. Their eventual collision created the Appalachian Mountains of eastern North America. This was no single collision. The mountain-building process unfolded in several distinct phases: the Tectonic, Akkadian, and Alleghenian orogenes. Each added new pulses of uplift, together forming a colossal mountain range that once rivaled the Himalayas in height. The collision caused intense crustal shortening, folding, and faulting. Deep within the crust, rocks were buried, compressed, and transformed by heat and pressure. Over hundreds of millions of years, Erosion gradually sculpted and softened the once towering peaks into the gentle, rounded hills we see today. Compared to the Himalayas, the Appalachians share similar features: folded sedimentary layers, metamorphic cores, and thrust faults, but they lack the deep crustal thickening found in the Himalayas. Today, the range is tectonically inactive, showing no major uplift or earthquakes, only the eroded traces of a once dynamic past. These calm landscapes preserve the remains of a fossil orogeny, a relic of the final suturing of Pangaea, when North America, Europe, and Africa were joined together as one vast supercontinent. The Appalachians stand as an ancient monument to Earth's restless history. They remind us that mountains are not eternal, even the mightiest ranges fade with time, yet their stories remain written in stone. Now, for our final stop, an even older origin, well-preserved and frozen in time, the Ural Mountains. Between 250 and 300 million years ago, during the late Paleozoic era, the East European craton collided with a series of microcontinents and volcanic island arcs, closing the ancient Paleo-Uralian Ocean. This process gave rise to the long, narrow Ural Mountains range, stretching over 2,500 kilometers and forming the natural boundary between Europe and Asia. The Urals are rich in ophiolites, metamorphic rocks, and remnants of volcanic island arcs. Together, these features record the full sequence of subduction, collision, and suturing that built these ancient mountains. The Urals formed when a continental margin collided with smaller land fragments and island chains, causing less uplift but excellent preservation. Because there's been little tectonic activity since the main collision, and a thick crustal root about 50 kilometers deep lies partly buried under sediments, the Urals remain exceptionally well preserved. Today, the Urals are tectonically inactive yet remarkably intact, a true geological time capsule that has remained largely unchanged for hundreds of millions of years. Our journey through time reveals the full life cycle of continental collisions, from the Himalayas, still rising through active convergence, to the Alps, complex and mature. The Appalachians, ancient and deeply eroded, and the Urals, fossilized yet perfectly preserved. Each tells a unique story of how Earth's crust responds to immense pressure. These collisions don't just build mountains, they shape climates and reshape the very face of our planet over millions of years. If you enjoyed this journey through Earth's tectonic past, don't forget to like, share, and subscribe, and click the bell icon so you never miss an update.